Deephaven community, back again with another weekly demo. This is April week 4. And first we have Christian showing off some nested JSON support that he's added. So here we go, Christian.
Hello, everybody. Hopefully you see my screen now. I just have here a Deephaven core clone. I'm going to go to the Red Panda directory, which is where we have the Docker compose that runs with Red Panda, which we need for Kafka. This is nested JSON as Kafka encoding. So I need Red Panda for this. So I'm going to just start the compose. Okay, so we have Deephaven and everything else needed running. I'm going to switch here and run our web UI. And I'm going to take the commands that I need to run from a script that we have. This is in the Red Panda examples Python directory, which is where I am right now. We have a script here that is called Kafka produce. And what the script does is that it can help you manually test and send some messages to Kafka so that they show up in Deephaven. So this is a script at the beginning. It has a big preamble with comments, and the comments contain the text of a script with a couple of test cases that you can run. And I added one for nested, so I'm going to be taking exactly that and cut and pasting from there. So what I'm going to do is that I'm going to do like a little grep command to take that script out of the Python code. So this is all the preamble at the beginning. And the first thing that I need to do is that I need to import the consume Kafka. So I'm going to just take that, go here, and run that. Go back to the script, and I need some types from this other import. And then I'm going to create a table using consume to table with JSON spec. So we're going to do that, and we're going to see a table show up. That is going to be empty because we haven't sent any messages yet, right? The interesting thing here, the part that is new, is that we have a spec that is going to be taking some nested fields inside JSON. So it's not going to be just top level JSON field with values. It's also going to be a field that has another JSON structure nested inside it. That is going to be this part here that is telling us to map /user/name to one Deephaven column that is going to be called username and /user/id to one Deephaven color that is going to be called user ID. What we're going to be doing here is, this is not probably the best way to call it, but I call it linearize the JSON data structure. So all these nested fields are actually going to float up to columns in the resulting table. So we are not going to be created a column that the column value itself is a composite. What we're going to be doing is that we're going to be taking the different components in the JSON nested structure and floating them up as individual columns on the overall table. That should be easier to work with, we think. So now I'm actually going to be sending one message. I'm going to be running Python to produce to Kafka, which should show up as a row, hopefully, if everything works, on our web UI. So I'm going to be running that. I'm going to show you the JSON string that we sent. I'm highlighting in that now. Is this string here? And the nested data structure is this user data structure here that you see there's an open brace here. And we have nested values of user.name, Pepo, user.id, 1, 2, 3, 4. And here on the Deephaven side, we see Pepo showing up as username and 1, 2, 3, 4 showing up as user ID. So that's it. That's our nested JSON. Only for the JSON nested structure, we need to actually specify this mapping where we say /user/name, float that up as username. You can see that for the rest of the columns, like symbol and side, we didn't have to specify a mapping. We're just using the default mapping for everything that is not nested, which should make things simple. So that's it for JSON nested. I wanted to do a really quick second thing, showing you an additional logging that we added for the server. You probably are familiar. I'm going to switch to that tab now. You probably are familiar with our Docker Compose logs for the server itself, right? Um, one of the log lines that is particularly interesting and we look at from time to time is this update graph processor cycle time line. So for instance, here we have a cycle time for the update graph processor of 854 milliseconds. That's interesting because how long it takes to do the update graph processor cycle is important. It's for how long the JVM was busy and the CPU was busy processing updates to all our graph of tables, right? And we have that configured to run once every second by default. You can change that configuration, but the default is once per second. It's important that it doesn't take more than a second because obviously if it does, then we begin falling behind. So it's something that for heavily utilized instances, we know that is an important performance metric to track. One thing that is interesting and that we have been trying to essentially correlate with how long it takes to do one update cycle, right, is the question, well, what if we actually are running out of memory? Because in that case, given that the JVM needs to do garbage collection, the JVM itself may be busy doing garbage collection during the time that we are running an update cycle, and our own code may not be running because the JVM needs to be like, tracking garbage. And I did experience this when I was working in the Materialize demo, Deephaven version, because I was trying to send a high message rate. So I was sending, I don't know, 100,000, 200,000 messages per second in Kafka, and reading all these messages in tables that accumulate in memory, right? In append tables in the consume to table call. Very quickly, just a few minutes, right? I will be running Deephaven for 10 minutes. I will run out of our default 4 gigabytes of RAM. So then I will increase the RAM, the heap size to 12 gigabytes. And then, I don't know, I moved from 100 to 100,000. And then, in 20 minutes, going back and forth and debugging, etc., I will forget. So I wanted a way to know, okay, I'm watching the cycle time. Am I hitting garbage collection or not? It turns out that what is easier to get as information is not exactly garbage collection. It's something that is called safe pointing, and we have safe pointing data here now in the log line. And in a second, I'm going to tell you exactly what it is, okay? But you can see here, aside from the cycle time 854, we have safe point time 79 microseconds. So of these 854 milliseconds, sorry, of these 854 milliseconds, 79 of those milliseconds were spent by the JVM itself. Our code was not running safe pointing. And this is the same, but as a percentage. So 9.24% is that 79 out of 854. So what is actually a safe point in the JVM? Well, at some point, the JVM needs to stop the world, stop every thread that is running your code, and do some things for its own sake. One of those things, and the most common one, is garbage collector. So every time the garbage collection needs to stop the world, some amount of the work of the garbage collector actually can happen in parallel. But for some types of garbage collection, which are the ones that actually we care about because it means our code is not running, our code is stopped. For getting to that code to stop, there are certain parts in the execution code in the JVM that are called safe points. And you can get the statistics, which is what we're printing in this log line, that says for how long that safe point did last, for how long we were paused. And that's what we're printing there. Most of the time, a same point is exactly the GC time. Less frequently, there are events in the JVM that need to create a safe point for other reasons. One reason could be, for instance, decompiling a class. If the JVM decides that the best way to execute something just change and there's some code running that is executing this class, it may need to change the running code, the assembly code for the methods in that class, and it will stop the code to be able to do that, and then the code will resume executing something else. There is a long list that is just one example. The thing is that most of the time, what you're going to be seeing there is GC. We say save point to be strictly right about what is there, but you can do a proxy in your mind and essentially understand that if you see a number there that is relatively high, you probably want to investigate further and confirm that GC may be the reason you're paused. Okay, that's it. That's my demo.
All right, cool.
So are the safe point values ending up in any of the performance tables?
No, but that's my next task. I'm going to add it to one. Amanda created the ticket, and we have been discussing about some ways to make that easy to use. So I have some code already. I have a branch already created and a PR in Flux, but I haven't finished it yet. But yeah, it's going to show up in a table.
Very cool. All right, next up we have Devin showing Java Mission Control for tracking leaks.
Hey everybody, can you hear me?
Yep.
Actually, let me share my screen. That's probably important. So this is JDK Mission Control. It's a Java application that primarily allows you to connect to running Java processes as well as analyze Java flight recordings. Java flight recordings are they're pretty self-explanatory, but there's a lot of interesting stuff in the JVM that can be saved and exposed via the Java flight recorder. And so I'm going to go through one use case that I found for it. Earlier this week, there was a bug report from a community member on our Slack channel about a Kafka append table causing out-of-memory issues after they had deleted the table. After a lot of debugging, we finally traced it down after using a Java heap dump. And if you've ever trolled through a Java heap dump before, it is a large, unwieldy beast. And luckily, the JDK Mission Control and Java flight recorders allow us to tackle the problem from a slightly different angle. The data itself is usually a lot smaller and more targeted towards interesting things. So I'm going to pull up a Java flight recording that I took earlier that demonstrates this issue and what it looks like. So this is a file that I recorded earlier today called the Kafka leak Java flight recorder. And the first thing you do that you see when you open up a Java flight recorder is an automated analysis. This gives you some good helpful tips of what may be causing some of this stuff. There's a lot of GC pressure during a certain time. There was some heap content, and you could go through this as maybe a first pass of what's wrong or what's happening in my application. Next thing that you can do is you can go to the whole application overview. There's a lot of information here, but I'll zoom in to kind of, I'll describe what the application was doing. At the very beginning, there was a ramp up where the Kafka stream started consumption, and then eventually the table was deleted, but you can see that over time this heap is still growing, even though we don't want it to keep growing. So you can see here is where we subscribe to the table, and so it takes, maybe a minute or so to get that full feed. But then, like we said, I deleted the table, but we still see these incremental heaps growing and shrinking. So the next thing we can do is we can go to the memory tab here. And this is kind of one of the most interesting things. So you can see most of our allocations happens right at the beginning. And it's telling us where our application allocations were. But probably the most interesting thing about the Java flight recorder is one of these things that tracks the live objects during different points in time. And so you can see here's all the allocations and here's all the different stuff that was reachable and sampled as live. So we don't care about the stuff that was alive at the beginning of the application. What we kind of care about is this tail where we don't want there to be allocation. So, or we don't expect the Kafka stream to still be going. So essentially what we can do is we can just select the back half of this table or of this timeline and see everything that was live during that. And the thing that was sampled most was this Deephaven API server console service. And if we go ahead and scroll down into that, it says, oh, there was some application listener that was there. We keep scrolling down and we keep scrolling down. And we get to a query table that was live. And this is exactly where the bug was that was discussed earlier. And it was much harder to find this query table when we were going through a heap dump. But when we look at this live objects view that the Java Flight Recorder presents us, and when we look at it through the JDK Mission Control, it's pretty easy, and it points it out as probably the most likely thing. So that is, one way to potentially track down a leak through live objects. And I will say there's a lot of other stuff that you can do with Java Flight Recorders. You can jump into garbage collections. You can jump into compilations. There's a lot of interesting stuff that you can get from the Java Flight Recorder. So, and this is also something that you can hook up through Docker Compose to our Deephaven server and get these Java Flight recordings in real time. And that is probably something I will be demonstrating at a later point in time.
All right, thank you, Devin. Very cool. That'll be useful for future debugging, I'm sure. All right, so now I'm going to show some of my changes for grid documentation. So on the web UI side, we have our components distributed and available for developer use, but we don't have a whole lot of documentation around it yet. So that's been one of the reasons that people have been slow to adopt it. So I've been putting together a docs page that has example code snippets, and then you can actually see the code snippet live below. So for example, this is just showing some static data and showing the output of that. And same with like other examples, like showing a quadrillion rows and that kind of thing. You can show it right in the docs, or in like group data, you can see how a tree example works, and you can actually play with it to see it in use. So I still need to fill out some of these other pages, but expect grid documentation to be emerging sometime next week. And I think that is it for this week. So we'll see you again next week. Bye, y'all.